All right. Looks like we're getting into the room. Well, greetings, everyone, and welcome to Color Literacy Forum number 13. I'm Luann Stovall, a member of the Color Literacy Project core team and host of the Color Literacy Forums. The forums offer a platform to share innovative research, teaching methods, and resources to expand 21st century color education at the university level across all disciplines, from design and the arts to humanities and the sciences. This project is a collaboration of the Color Literacy Project in partnership with the International Color Association, that's the AIC, the Intersociety Color Council, the ISCC, and Cumulus, the leading global association of art and design research. Before we jump in, though, please let us know who you are by putting your name, where you're joining us from, or your university or place of work in the chat box. An active chat box is highly encouraged in our forum, so please keep your fingers warmed up for comments and questions. We really like to hear from everyone and to know where you are and who you are, because we're all in this color community together. Thank you. This is the third forum in our 2025 series titled Facts and Myths About Color. The series delves into widespread misconceptions about color found in textbooks, including those from prestigious publishers, as well as in scientific and popular articles, magazines, and the internet. While the Color Literacy Project has previously addressed some of these myths, this series has taken a deeper dive with insights from experts across various disciplines. So the series has covered several topics. Forum 11 dived into the limitations of traditional color theory and explored how outdated models continue to shape education, their shortcomings in the classroom, and why an updated interdisciplinary model is needed. Forum 12 focused on misconceptions about color attributes, harmony, and meaning, addressing why a simple color wheel is insufficient for describing color relationships, how the hue paradigm falls short, and the complexity of color symbolism and its psychological effects. Today's forum number 13, that's MIX, MIXconceptions, Comparative Mixing, investigates the myth of color mixing. Why the idea that colors can be mixed in a straightforward way is misleading, and how comparative mixing provides a more accurate perspective. Before I introduce our speakers, let's review the timeline. Today's forum is 90 minutes long and is divided into two parts. Part 1 is the first hour. Each speaker will give you 25 minutes presentation. You're encouraged to type your comments and questions in the chat box during the presentations, but rather than take questions after each talk, we will have a moderated panel discussion with the speakers in part 2 of the program, and that's from 12 noon to 12:30 p.m. Eastern Time. Your questions and comments will be addressed during this session. So without further ado, I'm delighted to introduce our first speaker. The talk is Colors and Mixing. Paul Green-Armytage was born and educated in England, graduating as an architect. He had some 10 years experience as a practicing designer in England, Canada, and Australia, working as an architect, He has contributed papers at many national and international conferences, several by invitation, served as a member of the executive committee of the International Color Association, and as president of the Color Society of Australia. He is retired from teaching, but remains active as a researcher, writer, and educator. and has been a member of the Color Literacy Project team since its launch in 2020. In his summary for this event, Paul writes that yellow and blue make green, yellow and blue make gray, yellow and blue make white, yellow and blue make pink. To find out why and how, please welcome Paul Green-Armytage.
Thanks, Luann, and hello, everybody. Wherever and whenever you are. Here in Western Australia, it is 11 o'clock, just after, at night. I will now share my screen. If I can make it. Where's my arrow? There we go. Right. So, colours and mixing. Here are my topic headings. Stimulus and sensation. I will start by making the distinction between the stimulus, what enters the eyes, and the sensation, what is experienced in consciousness. I will demonstrate the processes of additive, subtractive, and partitive mixture of lights, inks, and paints that contribute to the stimulus. I will introduce a model for the attributes of appearance that are experienced in colour sensations. The term primary colours can be applied to the lights, inks, and paints that contribute to the stimulus. The term is also used for attributes of appearance. A colour gamut is the range of appearances that can be delivered by a given set of lights, inks, and paints, or paints. Complementary colours is a term for lights, inks, or paints that can be mixed to deliver an appearance of a neutral white or grey. The different complementary pairings delivered by different mixing processes can be resolved if the colour circle is elastic. To set the scene, I will begin with some audience participation. I will pose 2 questions. Please enter your answers in the chat. Question 1. Here is a disc divided into 3 segments, each a different colour. The disc is attached to a motor which will spin very fast so that the segments will blend and you will see a single colour. What do you think that single colour will be? Please enter your answer. I will allow 20 seconds, starting from now.
So, Paul, we are already receiving some answers to your question. We have Fatma saying that it will be gray, Mona saying that it's pink, Amber
fantastic.
Red, Eric saying that it's brown.
Okay, thanks. Thanks, Ingrid. Okay, time's up. Everybody ready? Let's see if you are right. I will now start the motor. No surprise? The colours on the disc are red, white, and black. And the single colour, when the disc is spinning at high speed, is a kind of muted greyish pink. It can be described as a bit reddish, a bit whitish, and a bit blackish. Question 2. Here is another painted disc, this time just 2 colours. Again, what colour do you expect to see when the disc is spinning at high speed and the colours are blended to a single colour? Please enter your answer in the chat. 20 seconds again.
We are already receiving green, gray, grayish green, light gray. We are about between green and gray.
Don't give it away, Ingrid.
Yeah.
You may prompt them.
Olive, pink.
Okay, all set. Righty-ho. I will now start the motor. Again, a kind of muted greyish pink. I wonder what you wrote. We've heard some of your answers and we'll maybe get some more at the end. When I showed this to a group of students, most of them said green. They knew from experience or from what they'd been taught that blue and yellow make green. Clearly not always. So what is going on? We need to break things down. Stimulus and sensation. The videos were made outside in the middle of the day and in overcast conditions. The light energy was well distributed across the spectrum. A kind of mixture occurs when light energy interacts with the painted surface. The pigment in the paint reflects some of the light energy and absorbs the rest. W.D. Wright explains, the coloring power of a dye or pigment is nothing more and nothing less than the power to reduce the energy in certain parts of the spectrum relative to the rest. In the case of the disc painted in segments of red, white, and black, the white reflects most of the light energy and the black absorbs most of the light energy across the spectrum. But the red segment and then the blue and yellow segments in the other disc reduce the energy in certain parts of the spectrum relative to the rest. The light reflected by the spinning disc that enters the eyes is the stimulus for color vision. Receptors in the eye respond to that stimulus and neural signals are generated for onward transmission into the brain. In the brain, something mysterious happens, and then we have a visual experience, a conscious sensation of color. The stimulus goes in and a sensation comes out. We can imagine some kind of transfer station in the brain. This is how Rolf Kuhne puts it. There continues to be a black box into which biologically produced correlates of physical stimuli disappear and out of which color experiences appear. This kind of black box has been defined in Wikipedia. In science, computing, and engineering, a black box is a system which can be viewed in terms of its inputs and outputs or transfer characteristics without any knowledge of its internal workings. The idea of Kuhne's black box is useful as a way to mark the point at which input is translated into output. When talking about mixing, we need to make the distinction between what is being mixed that contributes to the input and what is being mixed when we talk about the output. In the demonstration at the beginning, you saw what went in as the stimulus. You saw what were being mixed, painted segments on a disc, and you saw how they were mixed, being spun at high speed so that the segments blended. Then you saw the result, what came out, the sensation you experienced as a kind of muted grayish pink. If you had only seen the disc when it was spinning at full speed, you would not have known how the segments had been painted, but you could still describe the appearance of the spinning disc, which was essentially the same in each case, a muted grayish pink. And you could describe that appearance as a bit whitish, a bit blackish, and a bit reddish, a mixture of the appearance attributes, whiteness, blackness, and redness. When dealing with the input, I will talk about mixing lights, paints, and inks. I will talk about additive mixing, subtractive mixing, and comparative mixing. These all play a role in producing the stimulus. But I will also talk about what is being mixed in the output. We can talk about a color sensation as a mixture of appearance attributes. As scientists worked on the problems of color vision during the 19th century, they focused on what was going in, on the nature of light, the interaction of light and objects, the responses in the eye, and subsequent neural processing that led to Kuhne's black box. At the end of the century, Ewald Hering approached the problem from the other direction, on what comes out of the black box, conscious experience of color sensations. From his own experience at looking at his surroundings, Hering concluded that there are 6 fundamental color attributes, what he called Urfarben, that must have their counterpart in the nervous system associated with vision. Hering's Urfarben are white, black, yellow, red, blue, and green. I will return to Hering's ideas shortly. Before that, I will talk about the mixing of lights, inks, and paints that contribute to the stimulus. Additive, subtractive, and partitive mixture. Here, 2 spotlights are directed onto a screen so that the pools of light overlap. On the left, the spotlight is radiating mainly shortwave energy, which leads to a sensation of blue. On the right, it is mainly energy from the middle of the spectrum for a sensation of green. Where the pools of light overlap, The energy from each spotlight is added together, and we have a sensation of a brighter color that we might describe as turquoise or cyan. This is additive mixture. For this image, two diamonds were created in separate files. When the first diamond was printed, it reduced the energy in certain parts of the spectrum relative to the rest, and we have a sensation of blue. The paper was fed through the printer again, and the second diamond was printed so that it partially overlapped the first. The inks in the printer are transparent. We can see that the second diamond also reduced the energy, but in other parts of the spectrum, for a sensation of green. Where the two diamonds overlap, the light passes through both films of ink. The energy is further reduced, and we have a sensation of a much darker color that we might find difficult to name, perhaps a very dark turquoise or simply a very dark blue-green. Each film of ink subtracts some of the energy. This is subtractive mixture. When an artist mixes paints in the palette, it is also subtractive mixture. While white paint reflects energy fairly evenly across the spectrum and black paint absorbs most of the energy across the spectrum, other paints, as here, reduce the energy in certain parts of the spectrum relative to the rest. As one paint is mixed with the other, the mixture reduces more of the energy. Here you can see how the appearance of the mixture gets darker as more of the yellow paint was mixed in with the blue paint. Back to the spinning discs. When the discs are spinning, each segment reflects different wavelengths of light in such rapid succession that we are unable to register them individually. It is a kind of additive mixture, as the light reflected by each segment contributes to the stimulus. But the light itself is the average of what is reflected by each segment. This kind of mixture is sometimes called additive averaging or optical mixture. Here I will call it partitive mixture. Partitive mixture can also take another form. Here the checkerboard designs have been copied and reduced so that it is difficult to register the individual squares. The squares blend as the segments blended with the spinning discs. This kind of mixing can occur in the reproduction of complex designs and photographs, and it is exploited in the pointillist painting technique. To sum up, here are three ways of mixing lights and inks that appear blue and green: additive mixture, subtractive mixture, and partitive mixture. I will turn now to sensations of color and the mixture of appearance attributes. Hering's Urfarben are the basis of the Swedish natural color system. This is a system of color appearances. It has nothing to do with anything physical, such as paints or lights. But as a system of color appearances, it can be used to monitor the results of the physical mixing of paints and lights, as we shall see. In the system, a color's hue is described in terms of its relative yellowness, redness, blueness, and greenness. Its nuance, its position in the hue plane, is described in terms of its relative whiteness, blackness, and chromaticness. Chromaticness is roughly equivalent to Munsell chroma, but where chroma is open-ended as the degree of departure of a color sensation from that of white or gray, there is an endpoint in a scale of chromaticness. It is the most vivid color of that hue that can be imagined. Note that this and all reference points in the natural color system are mental concepts. They exist in the mind and not as anything physical. So it could be argued that an atlas of physical samples should not have been produced as being contrary to the principles behind the system. The system is in our heads and not on the pages of an atlas. When I was first introduced to the natural color system, I was struck by the fact that Greta Smedal had used the system successfully with her students in Norway several years before the publication of the atlas. While it may be true that you don't need the atlas in order to use the system, it is certainly true that an atlas is useful. But there must be a qualification. The atlas is described as an illustration of the system and not the system itself. It is necessary to stress that the physical color samples represent the averaged judgments of the original observers when they viewed color samples against a white background and under a standard illuminant. When viewing conditions are different, if the background or the lighting change and the appearance of the samples changes, the notation should also change, even though there is no change to the physical properties of the samples. To see if it is possible to use these conceptual reference points to describe a color, I taught the system to my daughter, Emily, when she was quite young, about 12, I think. I showed her a number of samples from the Natural Color System album and asked her to describe each one in terms of hue and nuance. We then found the color samples in the album that corresponded with her notations and found that most of Emily's judgments were close to the average judgments of the original observers. Primary colors. Central to discussions of mixing is the notion of primary colors. In the English edition of his book, 4 of Hering's Urfarben are translated as primary yellow, primary blue, primary red, and primary green. Hering defines these in terms of appearance. For example, his primary red is a red that is neither bluish nor yellowish. These are appearance primaries that are used as mental reference points when describing colors in the natural color system. They enable us to judge, for example, whether an orange is more yellowish or more reddish. This is a judgment of the attributes of appearance in a color sensation. But for most people, primary colors are all about the stimulus. They are physical. They are lights, paints, or inks that can be mixed to produce a stimulus that will result in a particular sensation. It is common for people to conflate these physical primaries with Hering's appearance primaries, and it is difficult to keep the two meanings separate. The idea that it is possible to mix all colors from 3 primaries goes back at least 350 years to the time of Robert Boyle. There are but few simple and primary colors, if I may so call them, from whose various compositions all the rest do, as it were, result. For though painters can imitate the hues, though not always the splendor, of those almost numberless differing colors that are to be met with in the world of nature and of art, I have not yet found that to exhibit this strange variety, they need employ any more than white and black, and red and blue and yellow. Boyle is referring to physical colors, paints, that can be used to produce all the rest. But he makes an important point in saying that while it is possible to imitate the hues, it is not always possible to match the splendor. Boyle recognizes that there are dimensions of a color's appearance beyond its hue. We can equate Boyle's splendor with chroma, or chromaticness. Color gamut. Artists and designers are mainly concerned with the appearance of their paintings or designs, but they need to know how to manipulate their physical materials in order to achieve the desired appearances. And if paints that appear red, blue, and yellow do not give them the splendor they want, they will need to use additional paints. A system like the natural color system can be used to reveal the shortcomings of a given set of paints and to indicate how such shortcomings might be overcome. A plan view of the natural color system can be used to plot the appearance of paints and paint mixtures. Here we can see the extent of the gamut, the range of colors that can be produced from mixtures of paints that correspond with the primary colors of tradition. The perimeter of the circle is for the most vivid colors that can be imagined. The further colors are from the center, the greater is their perceived chromaticness. Mixtures of each pair of paints are shown on mixture lines, and these are the most vivid colors that can be produced with those 3 paints. While it is possible to produce all the hues, chromaticness drops off sharply in the sequences from blue to yellow and from blue to red. For painters, this need not be an issue. They can use as many different paints as they like. From this figure, it is easy to see that the gamut could be extended by introducing additional paints between red and blue and between blue and yellow. Jennifer Goodman is an Australian artist who has about 100 different tubes of paint on her work table, and she keeps meticulous notes on the recipes for each color in her paintings. She has a firm idea in her head for each color. She starts with the paint that appears closest to her idea, and then mixes in a bit of this and a bit of that until she is satisfied. She kindly painted out swatches of the colours she was using for her current work, and I tried to match her colours on my computer. While there are no restrictions on the number of different paints that an artist can use, there are on the number of inks that can be used in a printer. It has been found that the largest gamut can be achieved with inks that appear cyan, magenta, and yellow, with black to sharpen the image. Cyan, magenta, and yellow can be called the printer's primaries. In this case, I was able to achieve close matches to Goodman's colours with these inks, since all her colours are within the gamut that can be achieved with the printer's primaries. On the right, you can see Goodman's swatches with their recipes, and beside them, my matched swatches with the percentage of each of the inks used to match her colours. Here is an indication of the gamut that can be achieved with the printer's primaries. The coloured shapes were cut from a printer's guide. The square shapes in the diagram are the yellow, magenta, and cyan inks printed solid. The inks can also be printed in small dots that cover a percentage of the paper. As the dots were smaller and smaller, more and more of the white of the paper contributed to the appearance, and it was possible to produce scales of increasing whiteness from the inks printed solid to the white of the paper in the middle. Partitive mixture plays a role here. Partitive mixture also plays a role in the hue sequence. It's in a kind of partnership with subtractive mixture. The sequences from yellow to magenta to cyan and back to yellow were produced by printing one ink over another in dots of increasing and decreasing size. In this design, you can see how increasing densities of yellow, red, blue, and green ink can produce a wide range of colors as each ink is printed over each of the others. To produce the design, I put the paper through the printer 3 times. I began by printing the yellows and blues. Then I printed the reds and greens so that they printed over the yellows and blues in the corners. Then I printed the central diamond shape so that each ink was printed over each of the others to complete the range of possibilities. The printer's primaries can be roughly duplicated in paint. Paints that appear similar to the printer's cyan, magenta, and yellow can deliver a more extensive gamut than the one delivered with the yellow, red, and blue of tradition. Here are the gamuts from mixing the 2 sets of 3 paints. More vivid greens and purples can be produced with the second set on the right, but there is some loss in the range of colours from yellow to magenta. When I was teaching at Curtin University, we used designers' gouache paints for colour study. Dale Rowney named 3 of the paints to make a connection with the printer's cyan, magenta, and yellow. On the left is the gamut that could be achieved with these 3 paints. To increase the gamut, we added brilliant red, brilliant green, and ultramarine, as you can see on the right. It turned out that this set of 6 paints is broadly the same as that recommended by Roy Osborne: magenta, orange, red, yellow, green, turquoise blue, and violet. While I have been talking about inks and paints, you have been exposed to thousands of little points of light being radiated into your eyes from your computer screens. Computers, like printers, are subject to limitations. They have just 3 kinds of element that radiate energy at different wavelengths to produce a wide gamut of colors. If you look at your screen through a watchmaker's glass, you will see a grid of pixels. Each pixel has 3 of these light-emitting elements. As each element glows more or less brightly, we see the different colors and images can be formed. I can't attach my camera to my watchmaker's glass, so I have prepared this to give an indication of how it works. The hexagonal grid is to represent the grid of pixels. The enlarged hexagon is to represent an individual pixel, which is divided into 3 parts, one each for the elements that glow red, green, and blue at various intensities for the different colors that will be seen on the screen. Where prints depend on reflected light and a partnership between subtractive and partitive mixture, the computer emits light directly into our eyes. The stimulus is a partnership between partitive and additive mixture. Red, green, and blue can be referred to as computer primaries. In this illustration, each of the red, green, and blue elements has equal influence on the appearance. This is to show how different colors can be generated. On the right, there is much more red than green and blue in the pixel. This is to represent the red element glowing more brightly than the other two. The red element now has a greater influence on the appearance of what will be seen on the screen. This is an indication of the gamut that can be achieved with the computer primaries, the three elements red, green, and blue. I created this about 30 years ago with my very first computer, which was an Amiga. The gamut of colors on the computer screen can be compared with the gamut achievable with printing inks. Complementary colors. Perhaps the biggest source of confusion about mixing is in the different results from additive, partitive, and subtractive mixtures. You were probably taught that mixtures of blue and yellow will result in green. That may be true of a subtractive mixture, but as you saw at the beginning, it may not be true of a partitive mixture. A good way to appreciate these different results is by establishing color pairs that are complementary. A color circle can then be organized so that complementary colors are opposite to each other. Colors are said to be complementary if they can be mixed to a neutral, white or gray. I found that the quickest way to do this was by partitive mixture with spinning discs. I painted a large number of discs and cut a slit in each so that the two discs could be interleaved and the proportions of the two segments could be adjusted. Here are the blue and yellow that could be mixed to a neutral gray. They are not the same blue and yellow that mix to a muted grayish pink. You can see that the two blues and yellows look slightly different. The blue and yellow on the right are each slightly reddish. So I had the complementary of blue by partitive mixture. That blue and that yellow mixed to a neutral gray. But when I mixed those two paints in the palette, the mixture appeared green. I tried mixing several paints with that blue. In the end, I found that I could mix a neutral gray with a paint that appeared a reddish orange. Meanwhile, I had been experimenting with additive mixtures of filtered spotlights and found that I could get white from an additive mixture of blue and yellow. So additive and partitive mixtures yield roughly the same complementary pairs, which can be quite different from the pairs delivered by subtractive mixture. This finding has implications for a color circle if opposite colors are to be complementary. What is the true complementary of blue, yellow, or reddish orange? This dilemma can be resolved if the color circle is elastic. The elastic color circle. As long as the sequence of hues is respected, the circle can be stretched and compressed to bring different colors opposite to each other. There can be one circle for additive and partitive mixture and another for subtractive mixture. Here on the left is the hue circle of the natural color system. In the other two circles, the intervals between colors have been stretched or compressed to bring the complementary colors opposite to each other. Complementaries established by additive and partitive mixing are opposite to each other in the middle circle. Complementaries by subtractive mixing on the right. The appearance primaries, Hering's Urfarben, are maintained as reference points. In each case, I kept the sequence from yellow to red unchanged, while the green moves a bit closer to yellow. The major difference is with the position of the blue and the number of steps from red to blue and then from blue to green. These diagrams can now be used to show how the results from additive and subtractive mixing can be so different. If you draw a line connecting the blue and yellow from the spinning discs, you can see how this line passes on the red side in the additive partitive circle and on the green side in the subtractive circle. To conclude, an exercise devised by Maggie Maggio for the Color Literacy Project enabled students to discover the difference between partitive mixture and subtractive mixture for themselves. Students choose two paints, a blue and a yellow. They use the paints unmixed and straight from the tube to paint the outer ring of colors for partitive mixture. Then they squeeze equal quantities of each paint into the palette and mix them to a single color for subtractive mixture. They use this mixture to paint the circle in the middle. The painted disc is mounted on a spinning top. When the top is spun, the central color remains unchanged, while the colors in the outer ring blend in a partitive mixture. Here is the disc spinning. Thank you. Finished.
Thank you so much, Paul. Joining everybody and giving you congratulations. We sure wish we could break for after this and have a workshop with you and get those discs out and the lights out and really play with that together. That's very helpful and really showing us what we're seeing. So thank you so much for that, Paul. And yes, thank you. We just learned from Paul that differences in the mixing processes, like inks and lights, cause differences in the results. Well, what happens when other non-traditional factors enter the mixing equation? What else could be considered an ingredient in the mixing process? To explore this new territory, let's meet our next speaker. Talk to Colors in Motion, Designing with Change. Marjan Kooroshnia is a pioneering researcher and associate professor at the Swedish School of Textiles, University of Borås in Sweden. With a PhD in textile design, she explores the intersection of color, light, and materiality in textile and fashion design. Her research pushes the boundaries of traditional design through innovative uses of smart colors, such as thermochromic, photochromic, electroluminant, and photoluminescent pigments that create dynamic patterns. She also investigates how the interaction between RGB light and colored surfaces can transform textiles into living, shifting expressions. By revealing new ways for textiles to change, her work opens up fresh design aesthetics, supports more sustainable practices, and inspires future directions in textile and fashion, interiors, and interactive experiences. Please welcome Marjan Kooroshnia. Marjan, the floor is yours.
You need to make me able to active my camera.
Oh.
Okay, now. Hi, everyone. Hi from Sweden. Thanks, Lauren, for the introduction.
That's perfect, Marjan.
Yeah, I'm not able to switch the slides. Sorry.
I know we'll get it.
Marjan, maybe you can try to share again.
The problem is that I lost my mouse again and I cannot stop sharing.
Try the right arrow key.
Oh, now, okay, let's see. Yeah, with that I can. All right, sorry. I remember the first time I held a thermochromic printed fabric. At first, it looked like ordinary, flat and still. But when I touched it, a hidden color appeared. The textile responded to me. That was the moment I realized color can be alive. This was not my first encounter with color changing. Some of you may remember mood rings from 70s or mugs that reveal color with the hot coffee. Back then they were novelists, but in design they became tools, ways to communicate, ways to tell stories. By the late 20th century, more smart colors appeared. Thermochromic colors that responded to heat, photochromic colors that wake up in UV light, hydrochromic colors that vanish in water, and electrochromic colors that spark to life with current. Suddenly, designers had a palette that was not fixed, but responsive. Working with thermochromic colors is like designing with time. They change color in response to temperature fluctuations. Each color has an activation temperature, the point where it begins to shift, fade, or reveal another color. Imagine a textile that blushes at your touch, a dress that brightens as you wear it, a scarf that blooms with your breath. Let's design a surface pattern. Every design begins with an idea, an emotion, a memory, or an image from the nature or culture. Sketches, photos, mood boards help translate the idea into motifs. Each motif can stand alone or repeat to form a rhythm across the fabric. Design software help us to refine, test, prepare the story for the fabric. Then color enters the process. A palette is chosen, bright, subtle, bold, or gentle. We consider how colors layer, separated, and interact with different fabrics, silk, cotton, polyester. Design meets fabric through printing, screen printing, digital printing, block printing, and each method leaves a different mark. Now let's use thermochromic colors for the same pattern and face the challenges. Traditional pigments are stable, thermochromic pigments are different. They respond to heat. The first challenge in designing dynamic surface pattern is that designing with them requires testing mixtures, observing behaviors, and predicting the reactions. At their activation temperature, thermochromic colors awake. They fade, darken, or reveal hidden layers. To print with them, pigments are mixed with the binder, creating inks that can be applied like the traditional colors. But unlike traditional colors, they move and transform. On top, you see traditional color mixtures. Blue and white will create the light blue. And below is the thermochromic color mixtures. Thermochromic blue slurry with binder would create a light blue thermochromic ink. Up to the non-heated state, they behave similarly. After heating or cooling, thermochromic colors shift. Thermochromic colors always shift from color to colorless through the heating and change from the light color to the more saturated color through cooling. When thermochromic colors are combined with traditional ones, the palette expands. On top, again, traditional mixtures. Light blue and yellow will create the light green. And below is the thermochromic mixtures. Again, light blue thermochromic and yellow will create the green. Non-activated, they look the same. After activation, heat makes green shift to yellow. As I said, always the color of the thermochromic itself would change from color to colorless, so what is remain is the color of the mixed pigment. And through the cooling, the color changed to the dark green. Here you see the mixture I tested, only thermochromic colors in different proportions before and after heating and cooling. Thermochromic colors mixed with the single traditional pigment. Again, I observed the effect after and before heating. Each mixture is ready to respond to touch, heat, or cold. And at the end, I define design possibilities offered by thermochromic colors. Here is one of my design. So I shall imagine how colors behave, which are visible in the non-activated state, which will be awaken, appear, disappear, or balance each other under heat or cold. This design considers all three phases simultaneously. So the textile tells its story through transformation. The result is the textile that transforms over time, almost like the choreographed dance. I mixed two thermochromic colors to create a secondary colors. Next, I mixed 5 thermochromics with 1 traditional pigment. At the room temperature, the colors look similar, almost identical. But when heat arrives, the hidden color emerges. The textile tells its secret. I combine this method of color mixing with the halftone and the CMYK printing method. At first, the print looked like a single quiet color, but with heat, the fabric burst into multiplied tones, revealing hidden colors. The next challenge using thermochromic colors to create a pattern is the quality of the chosen fabric. These colors can be printed on many textiles across materials and thicknesses. The textile itself shapes the color-changing effect. Thicker fabric, a slow heat spread, giving the viewer more time to watch the transition unfold. A silk organza, being very thin, changes almost instantly from color to colorless when heated. The next challenge is heat source itself. Different heat sources create different effects. Thermal energy, heating time, and heat distribution influence how colors, motifs, and patterns shift. For example, here is the knitted fabric with conductive thread. When connected to electricity, the conductive thread heats up, changing color and creating pattern. In addition to these factors, designers must consider dynamic color interaction when planning a design. Using Joseph Albert's concept of color interaction, a designer can understand how to create optical illusion and predict which one will appear. With thermochromic colors, dynamic patterns on textiles open the possibility for color interaction and illusion at 3 points in a time: in a non-heated state, in a heated state, and at intermediate moment between the two. Here are some examples. The bezel effect is an optical illusion. A single change in color can shift how we see an entire design. Picture two identical shapes, one bordered in white, one in black. Even though the shapes are the same, the black bordered one appears darker. Thermochromic colors bring a new twist to this idea. Imagine a red textile pigment surrounded by a thin black thermochromic border. In a non-heated state, the red reads as dark, the one on the left. But as the textile warms to the color's activation temperature, the black border fades to the colorless, and the red brightens, transform the perception of the design on the right. Another example is the color movement illusion that can be created by adjusting saturation or value, forming a continuous spectrum. With the thermochromic colors, movement happens in real time. As the temperature changes, colors shift and flow across the surface. Using smart colors challenges traditional design principles. Color can reflect moods, emotions, and time, and convey symbolism. For example, we said dark composition evoke night, mystery, and fear. This pattern has a dark brown appearance in its non-heated state. As the temperature increased, the color mixture activated and the print transformed from the dark brown to a vibrant, lively colors. In this way, the dark mood, evoking night, mystery, and even fear, shifted into a more relaxed, gentle, and inviting expression. The next challenge is the color system itself. Textile designers are visual learners. They learn by observing. Color circles and systems were created to represent color theory visually and verbally to help organize and predict mixtures and communicate choices to the colleague manufacturers and customers. But can this system capture thermochromic colors and count for heat? No. Traditional systems cannot describe how complex transitions can happen. To design a dynamic surfaces, color systems need to include heat and time, adding a new dimension to a color. Since no system existed, I created my own. I tested thermochromic colors alone, mixed with one traditional pigments, and even layered with different activation temperatures. Step by step, I documented their behavior in charts, making the invisible visible and showing how to mix, predict the outcomes, and communicate with each other. The other challenge is the terminology. A challenge in working with the thermochromic colors is the lack of terminology. How do we talk about their responses to temperature? Without proper language, understanding and communication become difficult. For example, on the left, we have the mixture of the thermochromic yellow ink with the red pigment, and on top is the binder. In the traditional way, we said that we mix yellow with the white to create a tint. But when I use the thermochromic inks and when I want to communicate with the students, if you heat it up, the color change to the lighter version, I cannot say you create the tint. And here you can see that there is a lack of the right terminology to describe it. And for those interested, my PhD thesis documents the full process, experiment, and discovery in detail about the thermochromic colors and is available online. I also explore photoluminescent pigment, which absorb light during the day and glow in the darkness. For example, in here on the left, you see the expression in the daytime, and on the right, the expression in the darkness. I also work with electroluminescent pigments, which glow with electricity. Here I had blue, yellow, and blue, green, and red pigment. I mixed them in the traditional color mixing, but they behave as a light, as an RGB light. I also learned that I can create different shades by playing with the voltage. I also work with the photochromic pigments, which change with the UV light. And I had magenta, yellow, and cyan, and systematically I mixed them together to create a pattern that can react to the UV light. Similar to working with thermochromic colors, each has its own behavior, design challenges, and a unique magic. Later, I explored textile under RGB LED lighting. In a dark room, 10 square meters with 3 spotlights on floor and 1 hanging from ceiling, I illuminated printed color swatches with red, green, and blue light. Complementary colors faded to gray, while matching colors glow intensely, almost self-illuminating. Light itself became a design material, creating alive surfaces. Light and pigment together become a storyteller. The next 2 videos shows how light and pigment told us the story of polluted oceans. Clear water turning murky, color changing, trace of the human impact. These experiments remind me design is not only form and function. It's about experience, surprise, and emotion. The smart colors are fleeting, alive, like the nature itself. Even today, when I watch a textile change with the heat or light or electricity, I feel the same wonder as that the first time. Thank you.
Okay, wow. Marjan, I was just thinking next generation color. I just thought of a couple things you said just about experience, surprise, and emotion that's happening with this. I also love, I'm sure we all did, light becomes a design material, light and pigment become storytellers. So just so looking forward to the next generation of what we can do. This is so important and so fascinating. So I'm going to move on to our next section here. It's our second part. This is our panel discussion. We have 30 minutes. Our moderator for the panel is Ingrid Calvo-Ivanovic. She's a color designer, researcher, and consultant, co-chair of the AIC Study Group for Color Education, and member of the Color Literacy Project team. Ingrid is joined in the panel by Paul and Marjan, and I will monitor your questions from the chat box. So without further ado, please welcome the panel discussion, and we welcome your questions.
Thank you very much, Luann. Thank you very much also to Paul and Marjan for these incredible presentations. I totally agree with what Luann said about the future of color mixing, understanding, overcoming the misconceptions with the first talk from Paul, understanding that take us to understand very different things and how we should understand color and experience color now and for the future. And what we had afterwards was a great case study of application with Marjan's work. And I think this provide the perfect stage for having an interesting conversation. So I would like to start with a question for Paul. I've seen also in the different experiments you show us with the spinning circles that it seems to me that proportion in color mixing has a very important role. You show us an example where you were changing the proportion in which you were combining blue and yellow, and the result it was totally different. So I wanted to ask you, this is maybe also a personal reflection on the different color theories that have addressed color mix in the past for centuries and centuries. And it seems to me that proportion has not been addressed properly in most of these theories. So I would like you to elaborate and or have your opinion on that, and to tell us, after your experiments and your experience experimenting with color, what do you think is the role of proportion for mixing colors?
Well, it's crucial. That's why I had the slit in those discs so that I could adjust the relative size of the different segments. And I needed to be able to adjust them so that they would mix to a neutral. So I'd have a go, a bit more of this, a bit more of that, and so on. And the same is true with mixing paints. I mean, if you've any artist will know that if you add one paint to another, the impact can be dramatic, and in other cases hardly at all. So you just learn how that works. I don't think there's any. I suppose you could work it out, but quite frankly, I think you just suck it and see. That's why I like a system like the natural color system. You can say, well, I haven't got what I want, so what do I do to get there? Well, I need to add a bit more of this or a bit more of that.
Yeah, and do you agree that it hasn't been addressed properly? Do you think it can be addressed? Can we?
I suppose it could be. I mean, I've done my bit with my spinning discs, but before I go any further, I just want to say that I just love your work, Marjan, and I can see there's a real challenge how to design a color order system that can take care of the fourth dimension. That's a challenge. So,
Yes.
About proportions. Proportions are very at the core important in transparency phenomena because they are dictated by proportions. It is about a century dealing with this model of perception in which the two colors, the front one and the back ones, seen through the first, are mixing and if the proportions changes, the impression of transparency changes. So it is very deeply modeled, these proportions in color mixture.
Thank you very much, Osvaldo. Osvaldo is also a consultant of the Color Literacy Project. Thank you very much for adding that to the discussion. And I will go with a question for Marjan before I give the word to Luen, also so we can see what are the questions in the chat box. Marjan, I totally agree. I think your work brings us to the new frontiers of mixing pigments, mixing inks, and try to understand how we can to understand if we are ready actually for as consumers, but also as artists or creatives for this concept that you presented about dynamic surface and with this adaptive and ever-changing colors. Related to that, my question for you is also related to the fact that you talk about the problem and the challenge of terminology. And if these surfaces and these results are going to be dynamic and changing, I wonder how do you organize your work or how do you talk about the result that you cannot predict when you are starting to work with the different pigments? So also I see you are working with students. So how do you manage that uncertainty when you are starting the experimentation process with the mixing?
The first time I was invited to teach thermochromic colors, I went to the printing lab and verbally I explained to them how it behaves. And none of the students capture what I'm talking about. So the next time I realized that, as I said, we are the visual learners. So I make the color swatches with the stable pigments, and I also print a big thermometer and I put it on the table. So visually I explain to them how the color transition will happen. But as I said, for the terminology, still I have an issue. So in my publications, I don't dare to call it that it changed from a color to light color, like yellow changed to light yellow. I use the NCS color coding.
Okay. I think that was a question that was also in the chat box. Someone was asking how did you specify the colors or which kind of system you were using. So that's clear now. Thank you very much. So Luen, do you want to address some question in the chat box?
Yes, thank you. Pat Lawson, it's a question, this would be to Paul. Is there an example of the elastic color circle? Will I be able to review the presentation again?
oh gosh, I first suggested the possibility way back in 1983, I realize. I think it's in the paper I presented in Boston. Yes, it was. I think the title of the paper was Relating Munsell to Other Systems in an Elastic Color Solid. So you should be able to get that paper, and if not, if you contact me, I can certainly send you a copy. But that's where I sort of articulated the idea. So you can actually morph from one color order system to another. But there's no way we'll reach Marjan's world with that. It's a very sort of static state of affairs. But you can morph from NCS to Munsell simply by stretching and compressing it, depending on what you want the color order system to tell you.
And Paul, part of that question answer, it reminds me of we would be able to, if we could, both that paper that you mentioned that you gave in Boston, and also Marjan, your thesis you said is available online. That would be, we would be able to. I'm going to ask Ingrid that too. Where we'd be able to post those links.
Can we put those on the website?
Yeah, I think we can, and we usually also upload the video of the forums after a week after the forum, and then we also include the links that we share or the documents that can be shared. So yes, absolutely, we can share that.
Okay.
And there's a question, Ingrid, for this is for Marjan. This is from Udo Schliemann. A question for Marjan: Are there thermodynamic colors that react at different temperatures, like room temperature or body temperature or below 0 degree? And are these colors readily available for purchase?
Yes, they're fairly easy to purchase them. Just remember, when you order, you need to choose the activation temperature. And considering ambient temperature is 20 degrees Celsius usually. So if you want them to change through the heat, order the one like 31, 45. And if you want to work with the cold, then you need to order something like 10 or 15 degrees Celsius.
Okay. I will go with another question for Marjan, related also in this envisioning the future of color and the mixing processes. So you presented that you work with electricity, with UV light, with time and temperature. So I think the key question then for me will become what else could be, because these are considered, or these in your work are kind of another, it's as they were other primaries of the equation, right, or other elements of the mixing process. So I wonder which other ingredients could be used in the future. Like, how do you see it? So what else could be consider an ingredient for the mixing color equation in your work that you are seeing, envisioning for the future? What would you like to explore?
You mean more than these smart colors that I already explored?
Yeah, and apart from electricity, UV light, so what do you think other elements or other techniques that could be used that we can try to imagine? Yeah.
Some years ago, Maggie introduced filters to me, like the polarized filters, Dacro filters, and I'm really interested in exploring those. And as you can see, again, you can see the trace of this dynamic change. It seems that my interest lies on the dynamic changes.
Great. And do you have you considered working with electronics? Have you integrated electronics to, or wearables, textiles, like electronics to the surfaces to the dynamic surfaces? Or you
Yeah, as you may saw in two of the slides, we incorporate the conductive threads. They are carbon threads. And then when you pass through the electricity, the carbon heats up, and then the heat will change the color of the thermochromic. And in that case, since we have the binding and structure, so the structure of the fabric and the color changing of those structure will create the surface pattern for us. So in the answer, yes, I also work with electronics.
That's
I've got a question. How quickly do those changes occur?
It depends on the heat source. As I said, if you use the hair dryer, it's in the blink of the eye, or the iron. But if you use the body temperature, it takes a little bit of the time.
Right. So to create something dynamic, you need to have directed heat.
Ah.
Wow. Opens up some wonderful possibilities. In the theater, think of that.
So, Paul, question for you. So how would you recommend teaching these different mixing processes? to arts and design students to avoid the problem of misconceptions?
Well, try it yourself. I mean, everything I know, I learned from doing it. One of my, public enemy number one to some extent in the Colour Literacy Project is poor old Johannes Itten. We're constantly having a go at him. But in his book, he implies that whether you define complementary pairs by additive mixing or subtractive mixing or by after images, you'll get the same pair. And I said, well, no, you don't. Did you check it out, Mr. Itten? I don't know. I wonder if he did. Anyway, and he also seems to confuse appearance primaries with physical primaries, because he defines his primaries in his book just like Herring. He talks about everybody with normal vision can recognize a red that's neither yellowish nor bluish. So here's a problem. Look, it's very, very complex, and it's a topic that constantly slips away from you. You think you're on top of it, and then it sort of slides out. I spent decades trying to nut it out. And yeah, it's totally enthralling. I mean, once you're hooked, once you're hooked on the topic, you're doomed, I think, because you'll never leave you alone. Anyway, so how to teach it? Well, I'm preparing a paper for our national conference in Sydney, which is coming up in early November, the end of October, and the title is Teaching Colour Without Teaching. And it's all about how to set things up for students to discover things for themselves. And I think that's the best way, because if you find something out for yourself, then it becomes your knowledge and it's much more precious, and it stays with you. I'm sure you must have done a lot of that kind of stuff yourself, Marjan.
Mm-hmm.
All your
Yes.
experimenting, you thought, oh, if I do this and this, I get that. And that's what I guess, is that what you get your students to do?
Yes, I have a famous question that everyone refers it to me. When I was a PhD student, my research question was, what if? What happens if?
Oh, beautiful.
So we also push our students to think about what happens if.
That's very, very
Fantastic.
interesting. Yeah, that's
Beautiful
maybe something we all need to ask ourselves when we are working with color, experimenting with color, right? So Luen, do you have any other questions for the chat from the chat box?
This was one of the early questions from Jose Cavano. Jose says, it is true that chroma scales are open to the right end in the Munsell and do not have a physical sample in the NCS. But don't you think that spectral colors, like color sensations arising from single wavelengths, can be considered the endpoint of chromaticity scales, at least for human color vision?
That's I guess sort of. I'd rather defer that to Osvaldo, actually, because you can actually get even if you stare at a color and get an after image and you superimpose that after image on the same color, you can get a super saturated experience. So there are a lot of frontiers that we haven't really explored. I guess the spectral locus in the CIE chart is one kind of limit, but I don't like to think of there being a limit. I like the idea of the color universe, if you like, being kind of open-ended, and you can go beyond into the world of hallucinations. Who knows? You can get to the limit of chromaticness in the NCS, but that's for surface colors. Then you can get fluorescent colors which can appear even brighter and beyond in your imagination, even further maybe. You can see Jose's face lighting up. There are two of you down there, Jose. How come you've got two? Anyway. There's a challenge for you, Jose. Extend Césaire into the fourth dimension.
Paul, that's related to a comment that Maggie gave, which is related to the elastic model. Maggie says that the 3D models we use in color literacy are elastic, and yes. Paul,
Yeah.
actually, would you comment on that? I mean, so because what that means, because we worked hard to like really think about what you've been talking about with the elasticity of how we can represent color.
Well, it depends what you want to get from a color order system. If you want to know what two colors or two inks, if you like, or two paints will mix to a neutral gray, then you structure the model accordingly. If you want to know after image complementary pairs is a little bit dodgy because I think there's a phenomenon known as after image color progression. The notion is that the after image of color A has the same hue as color B, but it sort of moves around the circle. That's something that hasn't been really explored yet. But a local artist has produced a beautiful color circle where you go all the way around in steps. What did you ask me? I've forgotten the question.
Well, that was related to elastic models. But
Okay.
yes, there is a question by Vincent Lacroix, and I'm wondering if he can ask that question. It's an answer to my question on complementary colors.
Well, it depends what you mean. There's no such thing as a single pair of correct complementary colors. There are three ways of defining that I'm aware of. One is by mixing, so mixing paints or inks or lights, and if you can mix them to a neutral appearance, then you can say, well, I've established a relationship and I should call that complementary. And the other one is after images. And as I said, that's a little bit, I'm not quite sure about that one. But broadly, if you get a complementary pair in after images, if you stare at them, they'll appear to change places in the after image. That can be quite impressive, but it's not quite spot on.
Okay. Well, and Paul, his question is complementary colors in the computer color spaces. The complementary relationship should be consistent. If two colors are complements, the relationship should hold, but it does not when going from RGB to lab. Why?
Well, they're different. They're modeling different aspects of color space, I guess. LAB is, and I'm not a color technologist, but that's about visually equal steps, I think, and it relates to the CIE chart. I think I'm out of my depth here, so I'll stop. Sorry. Yeah.
Luann, do
Still
we have
staring at me, Luann.
Sorry?
Yes. So I'm reading, so his comment is yes, but assume you keep the same relationship. I'm almost thinking, yeah, he said yes, but if you say it should add to neutral.
Well, if that's way of defining it, yes, and if LAB's opposite pairs will give you a neutral in the middle, well, then you can say, yes, I've established a relationship and I can call that complementary. Yeah.
Okay, cool. And there was a question related, this was for Marjan, and this was, Robin was asking about what happens when there's unstable colors or that you're using, unstable paints when you're heating them. How does that impact your work?
But unstable, you mean if it's like thermochromic colors?
What I'm getting, Robin's question was good work, Marjan. How does color changing paint impermanence affect your work?
I think I need a little bit of more elaboration on that.
Robin, are you available?
Yeah.
Okay.
Well, almost all of these color changing paints and inks are not permanent. In that I have a mug from 30 years ago that had color changing ink on it and it no longer functions. And my point is that artists usually want to create something that lasts. And how does that, the impermanence of what they're creating affect their artwork and what they're trying to portray with their art? Does it affect them at all, or does it not consider it and they just do it for the moment and then move on?
Well, it depends, but as you said, they are not permanent. Like these thermochromic inks, I never counted, but some people said that it works only 3,000 times. But we can, use them for the purposes, like encourage people to use something 3,000 times. And also, as a designer, we can design in a way that when they start to fade, some other permanent pigment will show up.
Okay.
So there are possibilities to play with it. So I never see this not being permanent as a limitation. I think it's the design possibilities.
Okay. Interesting.
I guess that what you are saying, Marjan, also is that maybe we need to be to start accepting for the future, also thinking maybe in sustainable design, sustainable fashion for the future, sustainable textiles. We maybe we need to start accepting the idea of color imperfection. And that color may change with time and may have also lifespan, right? And that's something. I think this is something that is very innovative as a concept, also because as I think Robin was saying before, we are kind of used to the fact that color has to be stable, and that's also that provides with quality or the value of quality for consumers and for people in general. So how we can, or how could we, this is maybe not, you don't have this answer, but the reflection will be, how can we start also having this conversation and trying to understand that color can have a lifespan, it can change, it can be imperfect. That doesn't mean there is not a quality or high quality, right? So do you, related to that, do you see your work on with thermochromic textiles as related, or maybe also fostering sustainable fashion design practices or textile design practices? So how do you see that?
You are completely correct. And in the textile and fashion design industry, you know that we are one of the most polluted industry. And there is a very high vibe on using the natural colors. But one of the biggest problem with using the natural colors is the fading part. And right now I have one PhD student using the fading as a design. So her thesis is designed for fading. And as you said, they are fade through the time. And again, we have the problem with the industry because none of the color system they use has been made for this unevenness of the natural colors and also the fading part. So they will also have the same problem as me, not having the proper color system for this kind of fading situation.
Yeah, not being able to predict how this will, how much time this would last, or
and what color they will get.
Yeah, exactly. Yeah, Luen, do we have if we have another question from the chat, maybe one or two, so we can then wrap up the conversation?
I will read the last question just came in. This is from Jose Charvaria. Color spaces are not typically defined around complementary colors because there are also at least 3 different definitions for complementaries. Just because a pair of complementary colors matches a geometry in one space, for example, a straight line through the neutral point, it doesn't mean the geometry or the colors themselves should hold in other spaces. So that's the comment.
That's the elastic color solid.
Okay, so just to close this part of the conversation, I think we have seen today very different challenges also in trying to shape and reframe our understanding of how mixing works and different mixing processes. So that pose us, most of us that maybe are color teachers, also great challenges on how to address that and how to tackle also the misconceptions that maybe ourselves in the first place, but also our students may bring to our classroom, and try to I understood from Paul's answers, also from experience, maybe experimenting with color is the way to tackle that and to change that. On the other hand, we see also in Marjan's work a lot of opportunities for the future and for this reframing our understanding of color mixing. Personally, I cannot wait to see what else will be in the future, something that can provide different effect for colors and or can be part of the color mixing equation. So I think this was all about these new frontiers of mixing, this understanding and vision in the future, and try to update color knowledge, which is also one of the most important things that we are trying to do with this color literacy project. So I will give the word to you and the stage to you, Luen, so we can close our session. And thank you very much for the interesting discussion.
Oh, thank you. And I just think all of us, a round of applause if you want to turn on your cameras to just say thank you to everyone. That was just a brilliant, so many ideas and thought-provoking and questions. So thank you to Paul and Marjan for sharing your research and ideas with us, and to Ingrid for moderating the discussion, and to everyone here today for being part of the forum. Before we adjourn, we want to invite you to keep an eye out for the final forum in this series. It will be in December. We don't have the specific date yet, but keep your eye out. It will be posted on the Color Literacy Project website, and we'll love to see you there. It will challenge the perception of color as a merely aesthetic addition, instead highlighting deeper communicative, functional, and psychological roles. So keep an eye out for that. We encourage you to visit the website, learn more about the project, resources, and exercises. And we just put a link in the chat box for all the previous recordings from the forums we've had before this. So have a colorful week. Thank you so much for being here, and keep in touch. Take care, everybody.
Bye-bye.